All right, good evening, ladies and gentlemen. Today we're going to talk about geometric sequences. And these are the same sequences that we were seeing before, but if you remember, we focused mainly on arithmetic sequences. Now we're moving on to the geometric. We'll talk a little bit more about the differences here in a minute, but remember we had recursive formulas and explicit formulas for these. The recursive ones where you had to use the previous term, and explicit was that we did not. So first we're going to take a look at the recursive formulas for geometric sequences, and that is a sequence defined by the recursive formula. Remember we had the braces. The top number was always g sub 1 equals something, and then g sub n equals, and then we wrote a little formula here. Now for geometric sequences, the pattern here is that they're going to be going up by a multiple of a number. So that would be this r, or this ratio, and the g sub n minus 1, remember, these replace them with a's, and that looks like arithmetic sequences. So a sub n minus 1 was the previous term. So here g sub n minus 1 is also going to be the previous term. So we're going to practice writing these. Now, if you remember, I was not too picky about you writing these parts out. I am going to be this time because we're a little bit more in depth with these. So just make sure, and this does the same thing every single time. It just says for integers n being greater than or equal to 2, because you already have one. One's done for you, so you want to start at 2. Okay. So this is where r is a non-zero constant and is the geometric or exponential, that's another word for these, sequence with the first term g of 1 and the constant multiplier r. So again, we're going to multiply things with r here, and that gives us our geometric or exponential sequence. Okay, so make sure you write this part down. We're going to be using it quite a bit today. Okay. The first things, they're going to ask you to give the first 6 terms and the constant multiplier in the geometric sequence. So we've definitely done the first 6 terms thing before, so that's easy enough. Now when you're listing out these terms, please make sure that you are aware that they actually give you the first term, so you don't have to write that one out. You have it, it's 3, so you just put a 3 here and that's your first term. You do have to go then find the next ones. Now we can do this easily here using our calculator. If you remember this way I used to show you, you always initiate the first term, so you just hit 3 and hit enter, and then you say, okay, well, what are we doing here? We're doing 5 times the term before it, so 5 times the answer from before, so second answer down here. Oh, I keep doing that, my goodness. Second answer, there we go. So you just say, take your answer, you're pulling it from the one above it. So here we're going to pull 3, and it gives us 15, which makes sense. 5 times 3 is 15. And here we're going to pull, if we hit it again, we're going to pull 15 and multiply it by 5. So we get 75, which is true. You take 75 and multiply it by 5. So since we need 6 of these, we have 1, 2, 3, 4, 5, 6, and those are your first 6 terms. If you don't believe me, go ahead and do it by hand. So let's just write all those down. So 3, 15, 75, 3, 75, 1,875, and 9,375. Okay, a little sloppy, but there's our first 6 terms. That's part of our answer. The next part they wanted to, since we got that done, the constant multiplier. Well, that's easy enough. What do we multiply all these numbers by? Well, 5, and it's actually in our formula right here where the r should be at. So that is easy enough. So you would say r equals, r for constant multiplier, that makes sense, doesn't it? Would be 5 here. So those are your first 6 terms, and your constant multiplier is 5. So we can box all that up. Maybe do it separately, because you probably have a line A and a line B for your worksheets on this. So those are your 2 answers. And we got the constant multiplier, so check that off too. Beautiful. Alright, now we've taken a look at recursive formulas. Now let's take a look at the explicit formula. Now, before we just kind of had to guess at these, but here we're going to have an actual formula to write these, which is going to be a lot easier, and we're going to like it. Trust me. That's the difference between arithmetic and geometric, because these, you got to stick to these. So in the geometric sequence with the first term g sub 1 and constant ratio of r, so those are the same. First term is always sub 1, and your constant ratio is the same one we saw as before. You take g sub n, which is whatever term you're finding for that n, equals g sub 1 times r to the n minus 1. And notice r to the n minus 1 is the only thing taken to that power, not the first term here. And then for integers n greater than or equal to 1, which again, we're going to need this part. I'm going to be very picky about it, because if you have anything less than 1, such as 0, you have 0 minus 1, which is negative 1, and that's a negative number. Not going to happen here. Not to a power. We can't use those here. So it has to be n bigger than 1. So from here on out, you got to have something like this for integers n greater than or equal to 1. Okay, write the first 5 terms of the sequence defined by this guy. Okay, now these were a little bit different than we were doing before. Remember, these we just had to do g sub 1 and plug in a 1 for our first term, because they didn't give us our first term here. Equals 8 times the quantity, negative 5, well, that'll be interesting. We have a constant multiplier of negative 5, to the n minus 1. Now, n again is the same n you put in here, so 1 minus 1. Okay, then we just have to figure out what that is. Well, that would be 8 times negative 5 to the, well, 1 minus 1 is 0. Ooh, here comes our little, anything to the 0 power is going to be 1. So this whole part is 1 here. So 8 times 1 gives you 8. Oh, look at that. I said they didn't give us our first term, but that looks familiar. Interesting. All right, g sub 2. G sub 2 is going to be 8 times negative 5, that's our formula, to the, now n here is 2, so we have 2 minus 1 power, which is 8 times negative 5. Well, 2 minus 1 is 1, that's easy enough, because negative 5 to the first is just negative 5, so negative 5 times 8 gives us negative 40. Now you might be seeing a pattern here, in that, oh, that's 0, that's 1. The next one will probably be 2, which you're right, because g sub 3 is 3 minus 1, which is 2. Now, also, we could be making our lives a little bit easier by dragging this guy back out and saying, all right, well, I already know g sub 3. I'm going to just plug this formula in here and substitute in a 3. So, well, I guess we'll write it out this one last time. So 8 times negative 5 to the 3 minus 1. That's why you can keep track of what term you're on as well as what the term it is. So let's grab our calculator here and I'll show you a fancy way to enter this in. So turn that on. Can't do it like this because that was for recursive formulas. So for explicit, you just punch this in here. And we could have started here with this first one if we wanted to, but I wanted to show you what was actually going on here. And enter it in just as you see it. So 8 times negative 5 to the, now you got to be careful here. This has got to go in parentheses, this 3 minus 1 here. So 3 minus 1 power. If you don't, it will not read it right. So keep that and you hit enter, and that's going to be our next term, which makes sense because we're just taking negative 5 another time. So negative 5 times negative 40 gives us a positive 200. So that's our next term here, so positive 200. And again. So now what I did, the reason I put this in here like this was because now I can do this little trick again where you do second entry and just change this. Well, the next one is going to be n equals 4, so I'm going to change that to a 4. Boom, there's our next term. So g of 4 equals negative 1,000. There's our next term. And how many do they want? 5. Okay, so 5. We'll have to do g of 5. But guess what? This will be easy enough. Second entry, change this to a 5. Boom. 5,000 is our next term, which you might have guessed that, hey, we needed to multiply that by a negative 5, giving us a positive 5,000, but hey, there it is. And is that all we needed to do? Yes, write the first 5 terms of the sequence defined by that. So, of course, I'd hope you write this out a little bit neater than mine. I'm not going to take the time to do it right now, but your first 5 terms are 8, negative 40, 200, then negative 1,000, 5,000. And notice our signs here are alternating. That'll come into play later. Alright, example 3. So suppose a ball is dropped from a height of 5 meters and it bounces up to 90% of its previous height after each bounce. Let h sub n be the greatest height of the ball after the nth bounce. So essentially, if we wanted to draw a picture, we were just starting out at a height of 5 meters and we hit the ground. Right? Sorry, that is a flat ground. And we bounce, and that means we're bouncing up to about 90% of our previous height. So we're about there. 90% of this height. 90% of this height, and so on and so forth. And it would keep going until it dribbled out. Okay? So That's the picture we're talking about here, and we're starting at this initial height of, well, it's 5 meters. So 5 meters here, so 5 meters. Okay, so it says write an explicit formula for h sub n. Now h sub n is the same thing as g sub n, so we're just going to use h for height here. So h sub n, and we got to go back and get that formula we had. Oh, explicit right there. Whoops, there we go. G sub n equals g sub 1 to the r, or times r to the n minus 1. So I'm going to just copy that. I remember this part. So g sub 1, r to the n minus 1. So let's remember that. So instead of h or g's though, we're going to have h. So h sub 1 times r to the n minus 1. Okay, and then we would write out, 4 integers and you can abbreviate int for integers. N is greater than or equal to, here we use 1. Okay, well, no, we're not done. I thought we were done, but we still have to plug in what the heck is our numbers. What are the numbers that we're working with? So our initial height is 5 meters, meaning our first term is 5. So we would say our first height is 5 here, so we say h sub n. Since our first term is 5, we put a 5 right here, times our rate here, our rate or our constant multiplier. Well, we're doing 90% each time. 90 here, 90 here, 90 here, 90 here, 90 here, and 90 here. So 90%, we're being multiplied all those times it bounces. So you would write that, of course, as a decimal, so 0.9, or 0.90 if you prefer, and then to the n minus 1. N minus 1, and then of course you would write comma, 4 integers, n being greater than or equal to 1. Okay, so h sub n equals 5 times the quantity, 0.9 to the n minus 1 power, 4 integers, n being greater than or equal to 1. Okay, so that's our explicit formula. That's all we had to do for part A. Part B says find the greatest height of the ball after the 10th bounce. So the greatest height is just the peak where it's reaching. So essentially we want the 10th bounce here. So we say h of n, or which is going to be 10 here because it's the 10th bounce, equals 5 times the quantity 0.9. We're just using our explicit formula up here. 0.9 times, or excuse me, to the 10 minus 1 power, which is just going to be the 9th power. We know that, so I'm going to go ahead and simplify that here. So then I just have to figure out what that is. So I'm going to enter it in just as such. 5 times 0.9 to the 9th power, and we hit enter, and well, we say that equals 1.94 meters, because that's what our unit was. And this should say approximately, so we'll make those squiggly. I already maybe looked squiggly, but there you have it. Approximately 1.94 meters, which makes sense because we started out at only 5 meters, so after 10 bounces it should not be that high. So 1.94 meters is what we have here. Okay, and we'll have to save this last example for the next video because we're just about out of time here. So please continue on to video number 2. Thank you.